So Fuhito is a star in the area of market design, still rising.
That's great.
So PhD in 2008 from Harvard University, and joined Stanford University as a faculty member in 2009, and a tenure in 2013. Okay. He's currently the director of Stanford Institute for Theoretical Economics. He has received many honors, including Sloan Fellowship in 2013, an Economic Theory Fellowship in 2015, and invited speaker at the World Congress of Econometric Society in 2015. Okay. He's on the editorial board of 10 economic journals, including JET, Economic Theory Bulletin. What else? There are more. Okay. So, Fuhito, please.
Thank you so much. Thank you very much for coming. So this is my pleasure to talk about the matching theory and its application to market design. So I noticed that, many of you are actually working in this field. So I'm a bit worried if some of you get bored. So in that case, you have two options. You can work on your own stuff, or you can, or you can ask me to speed up. So please feel free to sort of interrupt, and then if you want to talk, hear about some more recent stuff. I have a bunch of lot of material that I just prepared just in case and so on. So please feel free to ask me to sort of be flexible. Actually, let me actually ask a question. So how many of you have seen some matching in your class before? Okay. Okay, so most of you. So how many of you have heard of the Galen-Shapley's algorithm? Okay, about 60%. So let me be a bit fast, actually. Okay, good. So let me actually describe the algorithm and so on. But okay. So all right. So let's begin. So let me kind of skip the first part pretty quickly. Okay. So I have 90 minutes today and another 90 minutes tomorrow in total. So I'm really hoping that we do talk a bit about sort of basic stuff today, but then quickly go to the various topics that have been interested me and many others in this room. All right, so just in case I prepared, this is actually the same slide that I prepared for the public lecture too. So, so you can, once that you have seen this slide, so you can skip the public lecture later today. So just in case you want a lot of background information without math and so on, there's a very nice interactive book. So let me steal a little bit material from his book and talk a bit about, what the market design is, especially the matching market design is. But I think, many of you know this, so let me be kind of quick. Just let me remind you that, when I think of the kind of matching market, so this is not necessarily the typical kind of market that many past economics studies have been done, at least compared to, let's say, commodity markets, right? So Alex yesterday actually mentioned this to this audience. So, in the commodity market, you might expect that there's a supply and demand, and supply meets demand, then prices guide, to make sure that the amount of supply and the demand equals to each other, so the market is clear, and allocation is efficient, and so on. So everything is great. Okay, there are markets in which we may not expect this magic to happen, right? So in matching markets, so we could imagine things like certain labor markets, especially when the market is regulated. So one prime example that many of you have seen, I'm sure, is a market for new doctors. So the one big example people have been looking at is the U.S. medical or residency markets. So in this market, the residencies the market where the new doctors who just graduated from medical school need to find a first job. But this job, quote unquote, is also part of their training, right? So i.e., they work as residents and then under the supervision of more senior doctors. And as such, oftentimes it's sort of considered to be an half educational institution also, certainly in the US and many countries also. And the prices are oftentimes regulated, so the price don't seem to really adjust well. And the important fact about this market, this is an example of matching markets, is that, well, there are a lot of heterogeneity in preferences. So, and then the doctors might have a lot of geographical preferences where to work and what kind of institution to work for, and then but the residency programs also would like to hire good doctors, and sometimes they are concerned about the balance of the body of the residents. So sometimes in terms of gender, sometimes in terms of ethnic diversity, and so on and so on. So it's a pretty complicated market. And among other things, so it's not a simple task of where the residents can just show up and say, hey, I'm interested in your residency program, so I will work for you. The residency programs needs to agree to hire that doctor, that particular doctor. So it's a matching market, i.e., you cannot just choose your option. You should be chosen by the other side of the market too. It turns out that this kind of market is pretty prevalent, all right? So there are maybe two examples. So if you are a student in NUS, well, congratulations. So I'm sure that you just did not decide to attend the NUS. You should be chosen, you should be admitted to NUS, which I think you did. So this is a matching market. Even in labor markets, you cannot just show up in front of Google and say, hey, I work for you, so you should be hired by them. Okay. So this is what I mean by matching markets. So, okay. So two sides have preferences to each other. All right. So this kind of complicates the interaction. Among other things, you may or may not be, you may not expect the prices to do all the jobs. Well, even in labor markets where presumably prices, the wages can adjust demand and supply. I have already said a few things about some labor markets where the prices are kind of rigid. Even better example maybe things like college admission or school choice. In the public school system where tuitions are free, so you cannot expect the prices to adjust. It's oftentimes against the law, so you might need to somehow sort of administratively decide who can be placed where and so on. There are even more examples. Organ transplantation is a very recent example where a lot of attention has been placed. The story is that in the organ allocation, so there are maybe deceased donors or organs to be allocated. The buying and selling the organs are usually not is illegal. So the one is to still decide who gets which organ when, okay, and so on. All right. So this kind of market has a property that maybe the prices don't do all the magic. The organizer of the market may be a bit more careful about designing the market in such a way that, roughly speaking, we would like to get efficient outcome, nevertheless, and oftentimes the other concerns such as the fairness might be a concern. The big questions are, in that kind of market, what kind of designs work well? Of course, when we need to first decide and study what do work well even mean in this context. So we try to talk about these issues in this tutorial. Okay, so we present some theory, define the concept of desirability, and then see whether we can achieve it by a nice design. Any questions so far? Okay, so I guess this kind of thing is pretty much obvious to many of you. let me just quickly talk about the model. Okay, standard model based on these two papers. All right, authors' pictures are here. All right, so the standard model is very simple. So let me use the language of doctors and hospitals being matched to each other. Again, motivated by markets like the residency match. So doctors are denoted by numbers 1, 2, or I and J in generic case, and hospitals are in the capital letters in this talk. So they need to find a match, okay, the partners, all right. So I assume for most parts the matching problem is many to one, i.e. the hospitals could hire multiple doctors. Each doctor can, however, be matched with at most one hospital. Okay. So if you are interested in more general case of many-to-many matchings or the matching over the network, Alex gave a very nice introduction yesterday, so you might ask him about these models. Let me be simple, however, today. Okay, so many-to-one matching. So throughout, I assume that these market participants, players, have preferences over the other side. So the doctors have preferences over hospitals, and similarly, hospitals have preferences over the doctors. And possibly also the outside options are available. So doctors are free not to work for any hospital, and hospitals could leave some seats vacant. Okay, so matching is a function specifying which doctor works where, if any. Okay, nothing is so far surprising. Okay, so I believe many of you have seen the stability concept. Okay, so let's just refresh our memories quickly. So it's made by the two requirements, individual rationality and no blocking pair. So I say that matching is stable if it satisfies these two conditions. The individual rationality simply means that nobody is matched with something partner that is even worse than the outside option. Okay, more characteristics of this market, however, is the requirement that there be no blocking pair, where the blocking pair refers to a pair of a doctor and a hospital who are not matched with each other currently under the prescribed match. However, they would rather be matched with them. The idea is that, we would like to have a matching that satisfies the stability, because otherwise there are either an individual player or the pair of players who would rather not follow the prescribed match. So from the point of view of the market organizers, that's the matching that is not stable would not be sustainable. That's a theory. The thought behind the theory, the definition. So again, the interpretations are it encourages participation and the market could be maintained if the market produces a stable match. Connection to the core. So the core is the concept in cooperative games, which turns out to be equivalent in this context to the stability. So among other things, core is known to imply price efficiency. So it's another good thing about a stable match. Okay, and it can be interpreted also as a fairness consideration. All right. So here's an algorithm that finds a stable match. Okay. So again, can you raise a hand if you have seen the deferred acceptance algorithm before? Okay. Okay, so most of them. Okay, great. Okay, most of you have seen it, so let me just say that, so we think of as a game where the people submit preferences and then a algorithm run basically following what I just wrote here. So doctors apply from the top hospitals, and hospitals in each step tentatively accept some doctors and reject others and so on. The only interesting part of this is that the hospitals will always re-optimize when new application comes in, so the tentative match never becomes a final match. Okay, so that's why it's called the deferred acceptance. And the great known result is that, this algorithm finds a stable match. Okay, so I was about to explain why, but I guess you have seen the argument before, so let me kind of skip. The only thing I'd like to say is that intuitively, deferred acceptance will eliminate any blocking pair, because if the doctor would rather be matched with some other hospital than his or her final match, that means, according to the algorithm, he or she has applied to that hospital and got rejected, and according to the description of the algorithm, that happens only because, well, there are better doctors in that hospital. So the hospital is not interested in blocking with you. That's good. Okay. So why is that interesting? Well, theoretically, that seems to suggest if the market organizers ask people to submit preferences and then run the algorithm, deferred acceptance algorithm based on it, it will find a stable match, which we expect to be good. It turns out that in reality, people actually use this algorithm, and I already mentioned the NRMP, National Resident Matching Program example. So this is actually a very interesting case. It's a bit actually parallel to what Daryl talked before. So the NRMP is the organization matching doctors and residents. So they figured out on their own, without the input from economists, as far as we know, they adopted the algorithm around in 1950. The algorithm turns out to be equivalent to a version of the deferred acceptance algorithm. So that happens around 1950. So they tried a few versions of the algorithm. It used to be a more like an immediate acceptance algorithm when they first proposed it, meaning in each step the matching becomes finalized. But then that doesn't seem to be good. They thought that's not working well. And from our point of view, if you do the immediate acceptance algorithm, the matching is not necessarily stable. So there's a sense in which that people kind of knew that the algorithm should produce a stable match, well, without knowing even what stable match means, I guess. So the first paper formalizing this idea was, again, in 1962 paper by Gale and Shapley. So that's a sort of interesting coincidence of their solution. All right. So all these things are documented by 1994 paper by Roth. So even more interesting, there are other markets, some of which adopted the same algorithm. So the interesting story about the UK medical match is UK medical match, unlike the US medical match, they adopted the matching algorithm, but different regions were organized differently, so it's separately from each other. So some regions copied the US medical match in 1960s. Others also tried to copy the algorithm, but apparently they didn't see the detail, I guess. So they adopted a different algorithm, some of them unstable, and by and large, all these unstable mechanisms didn't work well, so they quickly got abandoned and so on. So all these things are documented by this paper in 1991 by Roth. So that also gives the idea that maybe this theory behind this stability and algorithm finding a stable match is useful. Okay. So over time, people began to think that this seems to be actually important concept. So these days, the economists are actually more proactive and then explicitly advising market designers to implement a stable match algorithm. So in particular, the use of DEA has spread over different markets, including, I try to talk about it a little bit, in school choice, for example. Okay. All right, any questions so far? I guess these are kind of familiar to most of you. All right, so another good thing about this DEA is that it's strategy proof. Meaning that its dominant strategy is incentive compatible for doctors to tell the true preferences. So there's no point in gaming the system from the viewpoint of the doctors. All right, so that's good. So the problem, however, is that this algorithm is not strategy proof, actually. From the viewpoint of the receiving side of the algorithm, namely the hospitals. So this is a very simple example. So let me actually walk through this example a little bit. So this table is meant to give the information of preferences. So, so I and J are the doctors, and I ranks A best and B second, and J ranks B first and then A second. Hospitals have 1 seat each, and hospital A ranks J, I in this order, and so on. Okay, so in this market, if you run the deferred acceptance algorithm, so I and J apply to A and B respectively, and they are both accepted. So the algorithm stops in one step. All right. But then imagine that hospital A decides to misreport its preferences. Okay. So pretending that I is not even acceptable to the hospital. Okay. Then what happens is the algorithm is a little bit different. So I and J applies to A and B respectively, but then A is rejected by hospital A. So I need to go back to the applicant pool and apply to second choice. Now B is faced with two applicants, J and I. According to B's preferences, I is more preferred. So the deferred acceptance feature of the algorithm tells you that, well, they should be rejected. So J goes back to applicant pool. J needs to apply to his second choice, which is A. And J is accepted according to the reported preferences of A. All right. So now compare the outcome for A. So under true staying, A is matched with best second choice, which is I. Under misreport, the A is actually matched with first choice. So summarizing, this is a profitable deviation on the part of hospital A. So it's a misreport is profitable, i.e. the algorithm is not surge proof. It turns out this is not an isolated example for this algorithm. There's an impossibility result saying that there is no mechanism that implements stable matchings in a dominant strategy in any compatible manner. Okay? So there's no stable mechanism that is surge proof for everybody. Okay. So it kind of gives a very negative feeling to all of us, right? So we thought that stable matching, implementing stable matching seems to working in some real life application, and we thought that the concept of stability might be actually helping to understand how to organize the markets. But then it turns out that to the extent that we cannot really, we should ask participants to supply information about their preferences, there's no way to actually honestly get the information. And of course, if the information, the input to the algorithm is wrong, then there's no guarantee that the outcome is stable according to the true preferences. Okay. All right. So that's actually a very quick go through of the basic theory. So let me talk about this last issue I mentioned, which is that the stable algorithms can't guarantee true staying by participants, and indeed, so that seems like a problem. So if we were to really use the algorithm to organize markets like labor markets or school choice and so on, we should worry about this misreport by participants. All right. So, however, so despite this theoretical possibility of misreporting, somehow the markets are running pretty smoothly. So this is a list of places where particularly the DA is used. So the NRMP, JRMP is Japanese version of the NRMP. So it adopted the deferred acceptance in 2003. Despite the fact, again, that it's already known by that time that the DA is not study proof. UK Medical Match has been using it. The same thing. APIC is a market for not medical students. It's an intern market for the clinical psychologists in the US. They adopted the algorithm in 1998. So again, despite the fact that by that time it's well known that the stable mechanisms are not study proof. So New York City and Boston and other school districts have adopted the EDA as well in the 2000s. So the question we like to ask is, okay, so why is there any sense in which, well, we can believe that the algorithm should work well despite the non-study proofness? The first attack is empirical, coming from the Ross and Penson paper in 1999. So they were, around that time, helping the NRMP, the US medical match, to potentially think of redesigning the algorithm. And in doing so, they observed in the NRMP data something interesting is happening. Okay. So roughly speaking, they have observed a certain sense in which the DA is not such proof, but approximately incentive compatible. So in particular, they looked at the data on submitted preferences in NRMP. So they had access to it because they were helping them organize the market. So around that time, in the 1990s, the number of hospital programs in this market are between 3,000 and 4,000. All right. So they studied this data and asked the question, roughly speaking. So pretend that these submitted preferences in the market are truthful. Okay. And then ask the question as to decide to pick up one arbitrary hospital and then see if there's any alternative preferences that the hospital could have reported, submitted to the system, and benefited by doing so, while keeping preferences submitted by everybody else. This number turns out to be surprisingly small. Among the about almost 4,000 hospital programs, the number of hospitals that could have been benefited by doing so are hovering around between 10 and 20. So there's a suspicion that somehow something about this market makes it very hard to profitably manipulate. At this point, if you have questions or comments, please feel free to say it. Yeah. So the balance of the market. So around this time, the size of the size of the hospitals are something like this. The number of doctors are about 20,000, and the capacities. So I did not have a number of the capacity here, but the number of the capacities are comparable. Comparable in the sense that I forgot the exact number. Sorry. So it's not that there are exact equal numbers, which you may be actually thinking about, because there's a paper looking at the case with balanced market and the unbalanced market, and what happens are pretty different actually. All right. So one thing that I think some of you have a puzzle face, and I believe the following may be a question that you have. Well, so Ross and Person's data study suggests that maybe the manipulation is small in this data set. Well, it sounds a bit suspicious though, right? Because, we started out asking a question as to whether people have preferences, the incentives to manipulate the preference, misreport, but then they took the submitted data as truthful and then asked the counterfactual. What happens if, for example, maybe in reality the hospitals are already manipulating so much that in such a way that somehow this artificial data has a property that according to that manipulated preferences already, the additional manipulation doesn't happen. Okay, so that's totally a possibility, and of course they are smart people, so they actually thought about it. So they did a simulation. So partly to make sure that this is somehow not tricked by the data, and also, even if it is true that in the NRMP data, in fact, in NRMP, it is in fact the case that the manipulation possibilities are small, we still have just one data point of the one particular market, so we don't know exactly what is going on and what it might be causing this small manipulation property. So by simulation, we could change the parameter of the market quite a lot and see what's going on. So they did the very simple simulation. So there are n doctors and n hospitals, and for simplicity, they assume there's only one seat in each hospital. All right. And then there's a key parameter K, which is the number of hospitals that each doctor lists in his or her submission. Okay, K is a typically small number. So think of, let's say, in an NP case, so that most doctors list only 10 or fewer hospitals in their list. Presumably because in order to even be considered by the hospital program, the doctor needs to interview with the hospital, and there's only so much time for doctors to do it because medical students are pretty busy. So each doctor only considers relatively small part of the market, right? And to that, subject to that constraints, they assume preferences are uniformly distributed, drawn from uniform distribution and IID manner. The key measure that they are looking at is P of N, which is a proportion of hospitals that can profitably manipulate submit false preferences and strictly benefit if others are telling the truth. So, okay. So here's what they found. I wonder if this is a good enough resolution. So the horizontal axis measures the market size, which is n in the simulation, in the log scale. So here's 10, here's 100,000 and 10,000, and vertical axis measures the P of N. Again, P of N is the proportion. So for each realization, they count the number of hospitals with the property that if that one hospital did some misreporting, gets something better than under truth telling, while everybody else is telling the true preferences, and divided by the number n, i.e. the number of hospitals. So, and different curves here correspond to different Ks. Again, that is the length of the preference list of doctors. So what you can find is, okay, so here's K equal 10 curve, here's K equal 15 curve, and so on. So one thing you can notice is that when K is larger, then the manipulation possibility is larger. But for each K which you have fixed, this measure of manipulability goes down steadily as the market size becomes larger and larger. So for example, pick K equals 15, which is a sort of similar to NRMP. When the market size is like 10 or 20, the almost 40% to 50% of the hospitals have at least one profitable manipulation. But then when the market size is 100, then this number has already dropped into something like 500 base point. Did I do it correctly? So then when the market size becomes something like 1,000, then it's very small. It's indistinguishable with 0. All right. And similar pattern can be found for any value of K. All right? Yes?
So your IID means both the preference of doctors and hospitals are random.
Yes, yes, right. So basically, yeah, everything is random, and but then for each of them, they count the like average over all the realizations. I mean, they have done a few draws. Yeah. Yes.
They knew that there were about 5 doctors per hospital, as you mentioned. They could also simulate for 5 doctors per hospital and 5 seats per hospital. Would the numbers look similar?
Very nice question. So yeah, so this is something that this particular thing does not tell you. Yes, so it turns out that so it turns out that the pattern is actually similar. But let's imagine that the number of the hospitals, each hospital has 5 positions. Then for each So let's say N still refers to the number of hospitals, but there are 5 N doctors. Then the number actually becomes larger in each of the realization, but pattern is similar. So actually, that's one of the things that I wanted to actually say. Actually, I'd like to say now, because this simulation tells you nice things. In particular, it seems that the large market helps the NMT manipulation, but then it doesn't tell us, for example, whether this pattern will be actually realized in the market with many positions per hospitals. So we would like to say something about that. Yeah. Yes.
Why you want to keep the K constant when you get the larger market?
Why do you want to keep K to be constant? Is that the question that you're asking? Yeah, that's actually nice. So one of the motivations they did was, I mean, this author, Ross and Branson, so they were consulting for the NRMP. So they wanted to see, so they wanted to basically take K to be sort of calibrated to the size of what you find in the NRMP. So that's one motivation, which is to keep K to be small. Another reason is actually it turns out that if we set K to be equal to N, which is to say that every hospital is acceptable to every doctor and vice versa, it turns out that the picture is rather different. In fact, so you can actually connect the dots from here, right? Sort of. And then the picture looks more like this, actually. So the manipulation possibility actually goes up and asymptotes to 1, actually. So it turns out that this feature that each doctor is interviewing with only a relatively small number of a fraction of the market is also important for actually obtaining this this property, i.e., the limit of manipulability. If I have a chance, I'd like to actually talk a bit about why there's a difference like this. So in order to help it, I need to give a little bit intuition when I talk about the theory. I try to come back. If I don't, please remind me. Yes?
What is the assumption that the preferences are ID across doctors?
Yeah. Yeah, that's also another kind of question I'd like to actually take on now, because so it has a lot of stylized assumptions, like one position each and uniform random distribution, random and so on. So just quickly, it turns out that it can be extended to a little bit more general cases, but some limit. In particular, there are cases of statistical correlation of preferences under which this result is not true. So, for example, imagine a very specific situation where every doctor is, so there are lots of hospitals, but let's say every doctor ranks the hospital 1 first and hospital 2 second, or vice the other way around. Then essentially this hospital 1 and 2 are like basically monopolists in this market. So they are basically, we are back almost to a situation with just 2 hospitals. So it's acts more like a small markets actually. So there's a sense in which we need to impose some condition in order to make sure that each hospitals are a relatively small player in the market. So let me actually come back to it too when I talk about why we observe this pattern in the theory part. Sorry. So this one is the average out of, you're right. So Pn is a random variable. So Pn, distribution of Pn. So actually, I do not remember whether these authors reported this. So let me try to remember. Actually, I don't remember it. So it's kind of concentrated for large value of n. I think that, but I don't remember well, actually, sorry. All right, okay, so 2 points. So coming back to 2.1, so based on this simulation, their conclusion, the authors, Ross and Pearson's tentative conclusion is maybe the large market is helping. Okay, so again, the data in NLP suggests that in their data, not many hospitals seem to be able to manipulate profitably, and maybe that is because markets like NLP has a lot of market participants, thousands and hospital and tens of thousands of doctors. And maybe this simulation also verifies this. This is a reason. Once again, however, we still don't know why at all, because we do not have a theory yet, and also we do not know whether this pattern is more general or not. So in order to make progress on this, let me talk a bit about theory as to, well, why we observe this pattern. We might observe this pattern. So think of let me not go into the details of notation and so on actually, but let's imagine that we are imagining a sequence of markets, and each market is indexed by n, which is the number of hospitals. So we have game 1 where there is only one hospital, game 2 where there are 2 hospitals and so on. The number of doctors could be also increasing. It doesn't have to be, but okay. And following the spirit of Ross-Pearson simulation, so let's take k to be a parameter again. So that's the length of the preference list of doctors again. So this short list assumption turns out to be quite important for the result. Okay, so the game is a simple one, and what you might expect. Each participant submits preferences, and then the deferred acceptance algorithm produces a matching. Okay, there's a private information which is the preferences of the participant. Each participant knows his or her own preferences, but only the distribution of preferences of others. Okay, so that's a setting. Without really going into much detail, so here's the result. Okay, so for take any epsilon positive, strictly positive, typically small number, there exists n, i.e. the market size, such that two thing becomes the epsilon Bayesian-Nash equilibrium. I haven't defined what epsilon Bayesian-Nash, but that's what you might expect. So the Bayesian-Nash equilibrium, epsilon Bayesian-Nash means the deviation will not get u more than epsilon payoff gain in expectation. So there exists two things by everybody constitutes epsilon Bayesian-Nash equilibrium for any market with more than n hospitals. Okay, so take some threshold margin of error epsilon, you can find a large enough market where two things will make sure that nobody gets more than epsilon payoff gain. All right. So, well, this roughly corresponds to this earlier claim or the observation in NLP and simulation where in the large market the manipulation gain seems to be small. Okay. All right. So that's a statement. So let me now give you a quick intuition of why you expect this to be true. Okay. So intuition is the following. So remember that we have seen that one example in which under DA, the hospital successfully manipulated, right? So hospital A, so remember that example. In that example, hospital A likes J and I, and then strategically rejected Dr. I, okay? So by declaring I to be unacceptable to the hospital. So what it happened, caused was I rejected by the first choice needed to apply to the second choice, and that caused more competition for the other hospital. And then, in particular, that led another doctor to be rejected, and in that example, Dr. J, and Dr. J needs to apply to the initial manipulating hospital. Okay, and that new applicants turns out to be a better match for the hospital A. So generally, it turns out that this kind of chain reaction is caused by strategic rejection in the deferred acceptance algorithm. it turns out that there's a sense in which this is the only reason that the manipulation is profitable, potentially is profitable, i.e., whenever the preferences configurations are such that there exists a profitable manipulation for a hospital, you can always find a chain reaction of that kind. So that turns out to be true. Okay, so intuition again. So by strategic rejection, that can cause a chain reaction that might benefit you. Okay, so it almost gives you why you may not expect this to happen a lot in the large market, because in the large market, what you expect is the following. So you are a hospital, you strategically reject somebody, then that causes a chain reaction of application and rejection somewhere else, but now the rejected at any step of this rejection chain, the next application for rejected displaced doctor is unlikely to be your hospital. Rather, because you are just one of the many hospitals in the market, rather the next application is likely to go somewhere else. Okay, but then in the large market, under our assumption actually, it's also the case that with high probability, there are a lot of hospitals that have at least one vacant position in their vacant position, and that in particular means that next application of this rejection chain and along the rejection chain is much more likely to be the application to one of the vacant positions in another hospital. And if that happens, there's no further rejection, so the rejection chain just stops. So, and the result for your hospital is that you have strategically rejected somebody, lost somebody, but received no new application in return. So you have not successfully manipulated. So in the large markets, again, so there are you are competing with a lot of hospitals with excess capacity, so you are unlikely to benefit. So this hopefully gives actually an indication as to why under some assumption this happens, and in other assumption it does not happen. So so I claimed for fixed k, the manipulation goes down with market size with k equals n, the figure is not more like this. So in order for this argument to work, among other things, you need to assure that with high probability at least, there are a lot of vacancies. And small k means that there are a lot of hospitals that doctors are not even applying to. So that actually guarantees that some hospitals are not getting a lot of applications. And so that's why this is actually helpful. When k is equal to n, actually, without manipulation, all hospitals are getting with k equals n, and each there are enough, the market is balanced, i.e. there are same number of doctors and the hospitals have all capacity 1, then actually there's no vacant position actually. So when you reject somebody strategically, then rejection chain never stops and very likely to come back actually. So that is part of the reason, at least, that the figure, in order for this argument to work, the k being small is also important. Yes?
Maybe this is a wild comment, but it seems like this, the likelihood of applying to another hospital with a vacant position is a probability that can be analyzed combinatorically and allow you to calculate the rate at which epsilon goes to 0 with n.
Yeah, that's... Yes, so this is actually how we proved actually. So we have a probability bound on, yeah, right. And it turns out that that's actually an important question because I pretended that this everything works perfectly. So in the general case, i.e., when in the most general settings, we managed to show this result. The rate turns out to be pretty low, slow actually. So the rate of like epsilon you can take is I think something like I think it was something like log n actually. So it's like one over log n. So it's not actually fast. So when we put something more like, okay, so when we assume, for example, the uniform distribution, the figure is much better. So in the uniform, I mean, we actually did a little bit more than uniform, but in the uniform case, it's more like 1 over n. So we are more comfortable in that case. Okay. So another thing I want to say, so uniform is not important because even let's imagine that, let's say the likelihood ratio of one hospital becoming a first choice by any given doctor, and let's say the least of this figure is bounded by some constant, let's say constant across market size, then the asymptotically the math works quite a lot like a uniform distribution. So we still get to this, and in particular the convergence. What would be problematic is actually that's really your question, previous question. So imagine that we have a big number of hospitals, but let's say with probability 99% or like increasingly close to 100%, the preferences of a doctor is such that hospital 1 and 2 are the first two choices and the uniform among them. Then this argument breaks down among other things, because if you pick this hospital which happen to be one of these two dominant hospitals, then when the hospital rejects the applicant, then it's very likely that the next application of this strategically rejected doctor will be the other of the dominant hospitals. And then if somebody is rejected from that hospital, then the next application is very likely to be my hospital. So even though nominally there are lots of hospitals, these dominant hospitals are very likely to be able to manipulate. So for that reason, we need some assumptions or sort of dispersion of the preferences among doctors in order for this to be true. Yes?
In RMP data, do we know what the fraction of hospitals with that composition?
Yeah. So in the 1990s data in NRMP, which Ross and Benson studies, there are about 4,000 hospital programs, and among them, about 1,000 of them has at least one beta position. So we feel reasonably comfortable that this may be big enough. I mean, 1 versus 1,000 is a big number. Yeah. Great. All right. Everything fine? Great. Okay. So if you are interested in more in the mechanics of this and also the assumptions, so like I emphasized, this argument has some robustness, but there are some important restrictions on when this conclusion is true. So there are nice papers by Samok Lee in Aristat and Ashragi et al. In operations research, studying further of these issues. So if you are interested, please feel free to ask and read these papers. All right. Okay. So another thing I'd like to talk about, now that we began to talk about the real medical match markets, there's another interesting issue when we look at this market in some detail. That's about the existence of stable matchings. Well, it might sound weird because I have told you that the deferred acceptance algorithm finds a stable match all the time. Why is the existence even an issue? It turns out that the markets like NRMP has an interesting feature. Among other things, they are married couples or married or seriously in serial relationship who would like to find a joint position. Okay, so which is couples usually would like to work in close to each other so that they can live together, or at least they can visit each other over the weekend. Sounds like a reasonable thing to do. All right. So reasonable assumption is that if we treat the couple as a unitary actor, they have preferences over pairs of positions. So first choice for them may be 2 positions in city A, a second maybe 2 positions in city B, and so on, but never in their rank order list, their preferences would show up 2 positions where the husband, let's say H for husband works in city A, the wife works in city B, where A and B are in totally different places. Right? So this turns out not to be an issue in the very early days of the NRMP around 1950 because, well, almost all doctors were men around that time. But then, you know, the medical profession is relatively actually quick in actually having a female workforce. So by the 1970s, the number has risen to something like 20%, I think. And now, among the current participants in NRMP, 5 to 10% of the applicants constantly declare as couple and go on the market together. In APIC, so this is a psychology market, the number is something between 1 and 2%. If anything, this number is actually vastly underreporting of how many doctors marry each other actually, because these markets are organized year by year, and this couples only refers to the couples who declare to be couples and ask to submit a preference like this in the system. So that means they are on the market in the same year, right? Okay. So in any case, these numbers are not like gigantic, but they are basically too big to ignore. And then we remember we have not specified what to do about people having preferences like this. All right. So there has been a lot of attempts by the NRMP and other markets trying to accommodate a preference like this. Okay. So the story is that in the early days, the NRMP just ignored the existence and forced them to apply as individuals. And you know, that algorithm is it should be expected to find an unstable match, right? Because, well, chances that the application by husband and wife are not coordinated at all, so it's very likely that the husband is in city A and the wife is in city B. Right, and unsurprisingly, the participation rate dropped dramatically around the 1970s. So they did a lot of attempts, and currently they basically allow the couples to basically register in their website system as a couple and submit preferences exactly of this form, i.e., the couples can submit a joint preference list. So that seems to be helping, but the problem is that actually there's no guarantee that even such an algorithm can help. Namely, actually, the problem is even deeper because the stable matching does not even necessarily exist once there's a couple. So this is a particular example. There are 1 couple and 1 single doctor and 2 hospitals. So you can actually check one by one to enumerate all possible matchings and find blocking correlation in this market. So that's a way to make sure that the stable matching does not exist. Perhaps more instructive here is that let's try to modify the deferred acceptance and see if a stable matching can be found. And I argue that the algorithm is unlikely to work in every instance, particularly in this instance. So imagine that if you are organizing in this market and think of modifying the deferred acceptance, then what would you do? Well, a reasonable thing to do would be, well, let the single doctor to apply to his first choice as in the usual deferred acceptance. Maybe you should allow the couples to apply to this pair of positions. Okay, so that sounds like a reasonable heuristic. Let's see what happened in this case. According to the hospital A's preferences, it likes H better than S, so the S is rejected. So S needs to apply to the second choice, which is B. Now, look at the preferences of B. So the B likes S better than W, so W needs to be rejected. Okay, at this point, So W needs to go back to the applicant pool. Should we stop the algorithm here? Maybe not. Why? Well, now the couple HW has only the husband to be matched with A and the W to be unmatched. And this option is not even individually rational according to this couple's preferences. Okay, so the reasonable heuristics to do should probably let the husband of this couple to withdraw his application. That sounds reasonable, isn't it? Have we found a stable match? The answer is no. Why? Well, now there's a blocking pair, which is S and A is a blocking pair, actually. So S likes, remember, S applied to A but got rejected because H was there, but now H withdraw the application. So seat in A is vacant. So reasonable thing to do is accommodate S to be matched with A, perhaps. But then, have we find a stable match? Well, the answer is no. Now, coalition made of this couple HW and A and B is a blocking coalition, actually. H is actually more preferred by A than S. Okay, but then look at this application. So this is exactly the first step of the algorithm we have found. So I was trying to sort of heuristically do the patchwork of how modifying the algorithm to find a stable match. It resulted in a cycle. Okay, so again, the key is the complementarity of preferences of these couple members cause some rejection, so the withdrawal of applications, and then that made the algorithm not to be sort of going in a monotonic manner, so the cycle can happen. Okay, so that sounds like a problem. By the way, this heuristics is actually pretty close to what is actually adopted in the NLMP and other markets currently, actually. So to the extent that is similar to the algorithm, so this seems like a problem that might be a concern in these markets. All right. So, but then I said, but then these algorithms are still used, and if anything, expanding. So, it turns out that despite this counterexample, in the data, stable matchings are often found. And actually, most of the times, stable matchings are found. In the NLMP case, so we do not have access to data anymore. So they are, compared to the 1990s, where they were very lax about the data sharing. So they cannot give us data at all. But then, so when we asked the organizers of this NLMP, so they basically said, so Elliot Peranson, one of the authors in Ross Peranson, is actually in this market. Actually, he's organizing, helping the algorithm. So he said, when we asked, so there are about like several dozens of markets using the same algorithm, and around that time when we asked, so they had maybe 15 years of data, so there are about 1,000 markets. Among them, he said that there were about the half a dozen cases in which the algorithm did not find a stable match. Probably that's not a bad number. So we fortunately got the data from APIC, so this psychologist market data. So they adopted the algorithm just described in 1998, and we had 9 years of data when we studied it. In each year's data, we actually found a stable match. So it sounds like, well, maybe we can actually believe that the counterexample, like the one I showed, is probably not representative of what is happening. And in particular, one possible conjecture might be in some reasonable assumptions over the market conditions and so on, the probability of finding, probability that the market allows a stable match may be high, roughly speaking. Okay. And so this is what we did in a paper with Parag and Ao. So the previous incentive result was from my paper with Parag. So the existence problem also turns out to have something to do with the market size. All right. So we basically wrote a market, model of market sequence of markets where the market grows with the index, which is very similar to what we did in this previous paper. But then there are a small number of couples in this market. Roughly speaking, what we showed is the following. As the market size goes to infinity, the probability of preference realizations such that the stable matching exists, this probability goes to 100%, as the market size goes to infinity. Okay.
This is fixing the proportion of couples in the population?
So yeah, so this is actually one of the things I will say a bit more soon, but roughly speaking, actually, this turns out to be able to be shown only in the case in which the couples proportion is actually going down even as the market size goes to infinity. So in particular, our paper actually made even stronger restriction, which is that as a proportion of market size, i.e., where market size again refers to the number of hospitals, the proportion of couples can grow at most, well, strictly slower than the square root of the market size. Later, Itaya Shiragi and his co-authors actually showed that this can be improved. I mean, there's a small difference in the modeling, but let's forget about it. The proportion can be shown for any sublinear case. The proportion goes down to 0, but arbitrarily slowly. And they actually showed that when there's a constant proportion of couples in the market, this claim is not true, actually. So actually, in that sense, actually, we will actually come back to as to why we actually need this small couples assumptions in order for at least our proof to work. Okay. So this is actually one of the important questions, actually. So let me actually say a few things. So when we wrote this paper, so basically the one-line conclusion would be that in the large market, stable matching should be found. Well, not so if there are a lot of couples. So in NRMP, there are like 10% couples and so on. There are other markets where this ratio can be even higher. So there's a nice paper by Peter Biro and others. So they are computer scientists working on matching. So they noticed the following. In Scottish markets for teachers, so teachers and schools are matched. The teachers actually need to teach two subjects, and they often have this like complementarity between like which subject to teach. So they act like a couples, and essentially every teacher needs to teach two things. So everybody is basically a couple. In that case, they actually did the simulation of this NRMP algorithm and found that their algorithm is very, with high probability, they failed to find a stable match. And then they thought about a different algorithm to find a stable match. So it turns out that interestingly, in their algorithm, in that market also the stable matching does exist, but not found by the algorithm used in NRMP.
Suppose that it's hopeless to get the probability of a stable match to go to 1, but you can get it to a reasonable number, like whatever, 0.8, 0.9. One would be drawn to ask, well, what will happen when there's no stable match? That is, something will happen. The world is not going to end.
Right.
And there will be some cost, or there will be some new algorithm that takes Has anyone analyzed that?
So not much, honestly. So first of all, in our situation, the question could be asked, but in a somewhat uninteresting manner. So let's imagine that, let's call that stable, the matching is approximately stable if the number of doctors involved in blocking is like proportion goes to 0, for example. Then trivially this market satisfies this condition because you can find a stable match in a hypothetical market without couples and then look at that matching, then only blocking involves couples. So by assumption the number of couples are small. So it's not too interesting to ask that in our setting. So there's a there are not many papers making more progress on that. One exception I can say is there's a very nice paper by Rakesh Vora and his co-author saying the following. So look at the market with couples. That market doesn't necessarily have a stable match, but they show that there's a nearby market in the sense that the supply of seats by each hospital is part of just a little bit in the sense of a constant bound, such that under that supply of the seats, a stable matching exists. So in that sense, that's one case. So that's a sense in which the market may be actually close to having a stable match. But it's different from probably what you have in mind, because I guess you might imagine like the approximate stable match where the number of people involved in match may be small and so on. That's differently framed, but
what you just described seems to address it, because it says in the somewhat unlikely event that you have a block, maybe the hospitals can spend a little bit of money to increase.
Right. Yeah. So that's how they interpret it indeed. Right. So oftentimes this medical match has a lot of subsidy. So in particular, maybe the government could subsidize a little bit to create a position, for example. Yeah. All right. So let me come back to this formulation and quickly tell you about the intuition. Okay. Why this is true. Okay, again, what is being asked? Okay, the claim is again, there's a sense in which the probability of the existence of a stable match is high. Indeed, the heuristic algorithm that I described earlier is going to find a stable match with some good probability. The reason, so think of the algorithm where DA-like algorithm, but imagine that we just set aside all the couples and find a stable match running DA in this market only with singles and hospitals. We know that it will find a stable match. Now, but then after that, only after that, add a couple one at a time, okay, and then try to readjust. Okay, i.e., so find a stable match, add a couple, and a couple apply to pairs of positions. That can cause at most two doctors being rejected from potentially two hospitals, and then these rejected doctors need to apply and so on. So using the words that I introduced, so adding new couples will cause two rejection chains at most. And then if this chain, like in the counter example, we saw if one of these rejection chains comes back to the original one of these two original hospitals, then we might be in trouble because that might result in cycles. Conversely, it turns out that if none of these rejection chains touches the original hospital and then stops, then the outcome can be shown to be stable. I mean, you will have found a stable match. Now, in the large market, remember, under our assumptions, there are a bunch of hospitals with a lot of vacant positions. So even these two rejection chains are likely to stop without actually coming back to the original hospitals. So basically, for the same reason that the stable the matching algorithm was not easily manipulable, which is the earlier topic that we talked about, the same reason tells you that adding just one couple is unlikely to actually result in a non-existence of a stable match. Well, what happens if there are more couples? Then we add one couple and equilibrate in this way, then add one more couple and then do the same and so on. So obviously, as long as the number of couples are very small, so even though not more than one, the same argument goes through. And hopefully this also tells you that you need a lot of restriction on the number, proportional couples also, because for example, if you have a constant ratio of the couples, then what happens is conditional on being able to equilibrate find a stable match for a submarket, except for this last one couple. Now let's add this couple to the market and let them apply. In the very first step, there are constant fraction of hospitals which may have a couple member. So there's a probability that is bounded from below by 0, such that the very first application of these two couples, the couple members, will result in a bad situation, i.e., some couple member is rejected, and hence the cycle might be initiated. So this is one reason that, at least according to this construction, we need a lot of restriction on the proportion of couples. So the paper that I mentioned, this Ashiragi et al. Paper, improved upon it, basically using the same argument, similar argument, but when the newly added couples actually finds this rejection chain touching the basically the hospital that you should not touch, then you actually change the order of application of which couples are added and so on. So they use a graph argument to actually find a sort of find a good order of adding couples one at a time, so that they improve upon improve upon the proportion of doctors, couples who can be in this market and still find a stable match with probability, high probability. All right, but let me not go into detail on that. All right. Okay, so there are a bunch of other large markets studies. So actually, so I don't plan to really talk about them, obviously, them all. So large market have been kind of like used quite a lot in different contexts in matching markets. So actually, coming back to Larry's previous question, so some of the papers, like my recent paper with Yongkuchi and Jinwoo Kim, and okay, I already mentioned this Nguyen Bola paper that about couples. So couples problem is a particular case of preferences with complementarity. So preference complementarity. In the couple's case, they would like to, they have a complementarity between two positions in the same place, the same location. We could ask similar questions for firms. So firms may have demand for complementary skills. So in such a case, so our paper and also the similar paper as read on Hatfield look at this problem also. It turns out that firstly, a stable matching does not necessarily exist. So in these papers, we also looked at the approximate stable match. So now the situation is such that maybe there are finite number of big firms and continuum of workers. Now it's on the firm side, and in this market, it doesn't seem to be so natural to assume that there are a bunch of small firms. So in that case, the probabilistic argument like the one I just showed does not apply here. So instead, we need to do something else. So it turns out that also, however, in this market with small number of big firms with complementary preferences and a lot of small workers, stable matching does not necessarily exist, but there's a sense in which the approximate stable matching exists. Here, in the sense that the firms, approximate in the sense that for any blocking coalition involving the firm and a bunch of workers, the firms are typically involved with a small number of workers. So to the extent that we might imagine that the firm's preferences are, the utility function is continuous, then small blocking with a small number of workers is likely to only benefit the firm only a little bit in terms of utility. So in that sense, it's approximately stable. So this is, I would not talk too much about it because the math is quite different. But let me actually quickly say why this intuition holds. So in the large market, we can imagine a limit where the market actually involves a continuum of workers, and the firms are matched with a distribution of different types of workers. And then so we assume, and hopefully it's not crazy, the firm's preferences are utility function is continuous, and then the choice behavior also is continuous in the sense that if the set of workers applying changes only a little bit, then the set of chosen workers are also changing only a little bit. So under this continuity assumption, what happens is now we are more like a traditional variation market actually. So with continuous preferences, like consumers with continuous preferences and so on. So basically we can invoke Kaktanit's theorem actually to find a fixed point of certain adjustment function. And that actually corresponds to stable match. So in the continuum market, where now the workers work almost like a divisible goods, the stable matching can be found. And then in the large but finite market, there's a little bit of discreteness making this exact stable match not to exist in this market, but it's close to it. So there's okay. So without going into details, so there's some still kind of not agreement on what kind of large market is a sort of right model of the large market. We have seen some probabilistic argument where everybody is small. I just mentioned a non-probabilistic situation where we find a approximate stable match. But in any case, so so it appears that the traditional models are so discrete that you can oftentimes find a lot of impossibilities, and it's not easy to deal with. So resulting in the large market seems to oftentimes recover positive results. So that's one of the messages, if I may. All right. All right. Okay. So so I have about 10 minutes. And I did not plan to talk about the next topic necessarily, but so if you have questions, it's a good time to spend the remaining time on this. Otherwise, I will actually maybe begin to talk about this the next topic. So if you have questions, please feel free. All right. Okay. Good. So actually, I have a relatively large amount of material. So let me actually begin talking about this. And continue tomorrow. So the next topic I'd like to talk about is what I call the matching with constraints. All right. So we have reviewed the standard matching problem where the product finds a stable match and everything seems to be working pretty nicely. When we really talk about the applications, then oftentimes the standard theory is not applicable. Well, we have just seen that if you have a couple in the market, then it doesn't work as nicely as in the standard model. So generally speaking, there are a bunch of the features of the market that makes it impossible to just apply the standard theory. And so one of such topics is what I call matching with constraints. Okay, so I say that the matching problem is subject to constraints when there are some constraints such that even though the matching is physically possible, the matching is declared to be, infeasible, unattainable, or unethical. So some law might prohibit certain distributions. So for example, the school with completely white student population and black population, for example. So that's by law prohibited to make such a matching. So that's one example. Which is affirmative action. We could imagine having similar affirmative action type consideration in terms of ethnicity, in terms of gender. In the UK medical match I mentioned earlier, there's a somewhat peculiar requirement in the 20th century, saying that the hospitals oftentimes demanded that there be at least one one female doctor, but not more than one female doctor. So that's another example. I would not say that that's a good thing to do necessarily, but that existed. Okay. So in fast forward in 21st century, the school programs. So in application to school choice, for example, oftentimes multiple school programs are being run in the same building. So if we model this situation to be a matching between students and the schools, then multiple schools are subject to common constraints that's coming from the space constraints, for example. Then the a standard model that I just described, where the earlier is not applicable. So the question is, for these kind of situations, can we extend the model theory to still get a nice outcome? So there are a lot of examples. So let me actually try to fix ideas. Okay, so here's a case study from Japan. So I already mentioned that Japan, like the United States, uses algorithm to match doctors. So DA was adopted in 2003. Okay, so that was good. But then, after when it was adopted, so some people began to complain. So they complain, among other things, that the algorithms asks preferences from both doctors and hospitals, whereas previously, prior to 2003 in Japan, basically the doctors didn't have any say, and the hospitals just decided where to send the graduate to the different hospitals. So now that the algorithm really tried to take into account preferences from both sides, some critics said that led doctors to not to go to rural hospitals and concentrate there on some big cities such as Tokyo. So, and critics said that is very bad because too many doctors are concentrated in Tokyo and not anywhere else. So they complained. Well, for my purposes, it's whether this actually happened in a large scale or not, so there's some debate about it. But for my purposes, what is interesting is that, well, government heard this voice and introduced a regulation in 2008, which I call the regional cap. So this is a regulation where the government, well, Japan has 47 prefectures. So prefectures are region, Tokyo, Osaka, and so on. For each such region, the government decides the upper bound of the number of doctors who can be placed, okay, jointly across hospitals in that region. So this is one example of what I call constraints. So this is the number. Okay. So these are the regions. So you see Tokyo, Osaka, and so on. There are 47. 47 of them. And the bars represent doctors. And this purple plus blue bar are the total capacity, which were advertised by hospitals in that region prior to the announcement of this regulation. And this purple bar shows the planned regional cap when they announced the regulation. So just to give a sense of the size, so this is pretty significant. So there are about, around this time in 2008, there were about 8,000 doctors and 9,000 hospital capacities. And about 20% were actually in Tokyo. So there were about 1,600 positions advertised in Tokyo, which is about 20%. But then the government considers that is too big. So now the regional cap says at most 1,300 doctors can be placed. 300 reduction. And the proportional reduction is pretty big for some other urban areas. Extreme is Kyoto, which is this one. So it says basically the a ratio of the new regulation compared to the previous number was about 50%, actually, cut in half. Okay. So the rural regions, which not many of you might have heard of, have more lax constraints. Some of them actually, according to the government's formula, actually the irrigation is actually negative. So basically it's not the computed capacity is regional cap is actually bigger than the number announced previous years. Okay, so this is a kind of a constraint, and in case you are not intrinsically interested in Japan, I don't see any reason not to. But there turns out that mathematically same kind of constraints happens everywhere in many different contexts, and geographically also. So the Chinese grad admission is one of the cute examples that I really loved. So maybe those of you from China may be able to correct, but the Chinese government decreed at some point in the early 2000s. Well, there are too many academic positions in China. Well, so people studying to become academics. They need more people who are doing like business school and law school and so on. So they basically said that in the next 5 years, the positions in the academic master's program should be reduced 5% per year in the total of 23% or something. And then while these numbers will be sort of converted to the non-academic professional education. So if we think of this in terms of modeling, it's like having two regions, one for all academic master's program in China, and the professional program in China is the other region, and there's a regional cap common to all academic programs. So that's one other way that this kind of constraint happens. And there are many other bunch of constraints that I could describe, but I think I'm out of time for today, so let me not do it for today. All right, so tomorrow I will continue talking about this kind of problems, and then describe what kind of problems happens and what the solutions are. Okay, thank you so much.